A very good morning to all of you. Myself Uma Sharma, Assistant Professor in ECE Department of Ajay Kumar Garg Engineering College. So, in today's lecture, we will discuss operational amplifier, DC analysis of second stage and output stage. This is in continuation with my previous lecture where I have discussed the DC analysis of bias stage as well as input stage. So, these are the content of this lecture, second stage and output stage, and these lectures, these topic I have covered in my previous lecture. So, if you have any doubt in the DC analysis of reference bias and input stage, so kindly refer the previous lecture. So, this is the IC diagram for 741 IC circuit diagram, where this represents the biasing. This is the input stage. Here in this lecture I will focus on second stage, which includes Q16, Q17 and Q13B transistor, as well as I will discuss the DC analysis of output stage, which include Q19, 18, 15, 14, 21, 23, 22, where some transistors will be used for short circuit protection circuit. That also I will discuss in this lecture. So, come to the topic. So, from the previous diagram, I have drawn the second stage only, where there are three transistors Q13B, Q16 and Q17, along with the resistance R9, R8 and a capacitor is used, that is 30 picofarad, but at the DC this will behave like open circuit. So, we will not include this capacitor in the analysis. So, first you should know what is the meaning of DC analysis. So, to do the DC analysis, we have to calculate the DC current and DC voltage, DC current and voltage at all the node of second stage. So, like for Q16 we have to calculate operating point like current and voltage. So, for Q16 I have to calculate IC16, for Q13 I have to calculate IC13B, Q17 I have to calculate IC17. So, for the calculation part, we have to use some previous values, like this circuit is definitely connected with another transistor, and if you look at this diagram, this Q13B is connected with the Q12, where the current is represented by I reference. So, to do the DC analysis of second stage, we should remember the value of I reference, because I reference will be used in the DC analysis of second stage. So, let us start the DC analysis. So, if we neglect the current flowing in this direction, so this terminal is connected with Q23, this transistor is Q23. So, if we neglect the base current of Q23, then from the diagram you can see that the collector current of Q17, this is the collector current of Q17. So, I can write it like IC17. So, just a second. Let me remove these things so that we can do the analysis. So, IC16 is the current which is going at the collector terminal of Q17 transistor, and this is approximately equals to the current provided by the Q13B, because we have neglected this current. So, let us mark this current as 0. So, we have concluded that IC13B is equals to IC17. I can write IC17 is equals to IC13B. So to calculate IC13B, as you can see from the diagram, this is a double collector bilateral transistor where the scaling current of Q13B is 0.7 times of I reference. I reference is what? The current provided by the Q12 transistor. So the value of I reference we will use from the previous analysis, and easily we can calculate the value of IC13B just by multiplying I reference by 0.75, because in this transistor the scaling factor is 0.75 Q13B and Q13A, this scaling factor is 0.25. So overall the IC13 is equals to IC13A plus IC13B. So by multiplying I reference with 0.75, we will get 550 microampere. So this is the value of this current IC17. Now we have to calculate the value of VBE17, because I have we have to calculate current and voltages, DC current and DC voltages. So to calculate VBE17, we can use the formula, because we know the value of IC17, and IC17 can be written as, from the transistor current equation, IC17 is equals to IS e to the power VBE17 by VT. This is the current equation of transistor. So from here you can calculate VBE17, which is equals to VT ln IC17 by IS. So that is equals to IC17 by IS. So in this expression we know the value of IC17, that is 550 microampere. We know the value of IS, and IS is equals to 10 to the power minus 14 amperes. VT is nothing but KT by Q. VT is equals to KT by Q. So by putting the value of K, that is Boltzmann constant, temperature and the charge, we can calculate the VT, that is nearly equals to 25 millivolts. So by using all these values, we can calculate the value of VBE17, and that is equals to 618 millivolts. So this is how we have completed the analysis for B and Q17. Now I have to calculate the current flowing through this transistor Q16. That means I have to calculate IC16. Okay. So let's see from the diagram. If I write the current equation for IC16, so you can see from this diagram IC16 means this current, that is nearly equals to IE16, and if this is IE16 at this node, this current is going in this direction as well as in this direction, right? So the current can be, so we can apply KCL at this node, and IE16 can be given as IB17, this current component IB17, and here this current can be written as IR9, that means current flowing in the R9 resistor. So we have to solve this equation to get the value of IC16, which is equals to, nearly equals to IE16. So let's see how we can calculate. So in this diagram we have to calculate this equation. So for that I have to calculate IR9, because VBE17 is this current and we know the value of IC17. If I divide IC17 by beta, then definitely we will get IB17 directly. So this current component we can calculate directly, but to calculate IR9 we have to apply KCL over there. So just apply KBL in this loop, so you can calculate the value of IR9. So here let's say the value at this node is represented by VB, base voltage, and this IR 9 is nothing but VB, this voltage, minus, this is minus VEE. So direction, if the direction of current is downward, then that will equals to VB minus plus VEE divided by R9. So we know the value of VEE, but we don't know the value of VB, base voltage. So to calculate this voltage VB, we have to calculate the value of this base voltage. Again we have to apply KVL. So apply KVL over there. So we can write VB minus this voltage VBE 17 minus IE 17 into R8, and again this is minus VEE, this node is connected with minus VEE, so that will equals to plus VEE. So from here we can calculate the value of VB, that is equals to VBE 17 plus this IE 17. I can equate IE 17 with IC 17, and we know the value of IC 17. So here I can write IC 17 into R8 and minus VEE. So if, let's say this is equation 1 and this is equation 2. So just putting the value of VB in equation in this term, actually this is nothing but IR9. So just by putting the value of VB over there, we will get this expression. Like you can see in the previous slide, I have written that IE is equals to IB17 plus IR9. So in the place of IR9, I can write this expression, VB plus VE by R9. So just put this equation, the value of VB over there, you will get this expression. So here in this expression, now you know that VB17 we can calculate easily, just dividing IC with Vita. Definitely we know the value of IE17, R8, VB17 and R9. So just by putting all these value, we can calculate the value of IC16, and which is equals to 16.2 microamperes. So this is how we have done the DC analysis of second stage. Now come to the output stage. So this is the circuit diagram for output stage, where I have excluded the short circuit protection transistors. So these are the transistors purely used for the purely used for the output stage. So here Q14 and Q20 are the transistors which are having 3 times more area as compared to all other transistors in this IC, because these are the output transistors, and we know that at the output terminal we want that circuit should supply large current at the lower power dissipation. So to supply large current we require large area, and definitely we require that the impedance matching should be there. So to fulfill the requirement of impedance matching, we have used this transistor Q13, which is a emitter follower. Emitter follower means having infinite input impedance and 0 output impedance with a gain of unity. So generally we use the buffer at the output stage. So here also you can see that the output is taken from the emitter. So Q14 is again behaving like a emitter follower, and definitely the Q20. But these transistors are connected in the different fashion. If you remember, the Q combination of Q14 and Q20 are making a class AB amplifier. This combination is known as class AB power amplifier. And class, because this is the output stage, so definitely we require to use power amplifiers. So start with the analysis of this output stage. So definitely now we have to calculate IC, the parameter which I have to calculate it. I want to calculate IC 13A, IC 19, IC 18, IC 23, IC 14 and IC 20. These are the current component which we want to calculate while doing the DC analysis of this output stage. Okay, so in the previous stage we have seen that we have used the Q13B transistor for the biasing of second stage. So here we have used the Q13A transistor which is having a scaling current of 0.25 of I reference. So the value of I reference we are already have. So just multiplying this I reference with 0.25, we can calculate the Q13A. Now let's see this network which including which are having Q18 and Q19 transistor. So if you see that these two transistors are connected in series, so and they are connected in between base of Q14 and base of Q20. These two transistors, or I can say this network, is used to provide the double base voltage over there. So that means this network is used to enhance the base to base voltage of Q14 and Q20. So now we are having this current which is incoming in this network 0.25 I reference, and this is the output current. So considering that ideal case Q18 and Q18, so the current flowing through these transistors, if current dissipation is less or actually zero, this inward current will be equals to outward current. So that means 0.5 I reference will be equals to 0.5 of I reference, which is the current of emitter current of Q23, considering that the current going in this transistor is equals to 0. Again, considering that the current going in this transistor is 0. So if current in the base of Q14 and Q20 is 0, actually it is very small current, but we are considering the ideal case that IB is equals to 0. So if base current of these transistors is equals to 0, then I can equate the output current of Q13A with the current of Q23. In between we have to calculate these current components. So let's see how we can calculate. So the current by Q13A will be equals to 0.25 of I reference, and that will equals to 180 microamperes. So to calculate the current in the 18 transistor IC18, just assume that the voltage at this node is VBE 18, and just assume that the value of this VB is equals to 0.6 volt. So by assuming this 0.6 volt, we can calculate the current in the R10 resistor, because if the voltage across this node is 0.6 volt, we can calculate IR10, that is equals to 0.6 divided by 40 kilo ohms. So directly we can calculate the value of IR10, and that is equals to 15 microampere. Now from the diagram we can see that the total current minus the IR10 current is equals to IC18. You can see from here IC18 is nothing but the total current minus this. So that means this current. So here we can calculate the value of IC18, considering that it is nearly equals to IE18, that will comes 165 microamperes. If I calculate the value of VB18 again using this expression, like IC18 is equals to IS e to the power VBE 18 by VT. So using the value 165 microampere, IS is 10 to the power minus 14 e to the power VBE 18 divided by VT 25 millivolts. We can calculate the VBE, and that comes 5 0.88 millivolts, which is approximately equals to 0.6 volts. So this assumption we have made is almost correct. Now calculate IC19. Definitely that will be equals to 15.8, because VB18 is equals to IC18 divided by the beta, where beta is the 200. So that will comes 0.8 microampere. So this is how we can calculate IC18 and IC19 and IE19. And if we have the value of IC19, then definitely by using this formula we will calculate VBE19. I hope now you are able to understand how we have calculated all these values. Now come to the final part, that is including Q14 and Q20 transistor, means output part of the output stage. So to calculate the current in Q14, that is IC14 and IC20, just calculate the base to base voltage. So VB18 we have already calculated, VB19 we have already calculated, and you can see the value of VBB from there. This is the base of 14 and this is base of 20. So VBB will equals to VB14 plus, this can be written as VB14 plus VBE20, as well as that can be written as VB18 and 19, because the total voltage which appear between base of Q14 and Q20 will be equals to the total voltage of this network, and the voltage of this network is VB18 plus VB19, because these transistors are connected in cascading. So here we can calculate the value of VBB, which is equals to 1.118 volt, and just writing the second equation, that is VBV will equals to VBE14 plus VBE20. We can equate this equation by this, because VBE can be given as VT ln IC14 by IS14, and VBE20 can be written as VT ln IC20 upon IS20. Now we know that the transistor Q14 and Q20 are identical transistor. So the current in IC14, that means the current in Q14 is equals to the current in Q20. So if I equate IC14 with IC20, we know the value of VBV, which is 1.118. We know the value of VT, IS14, IS20. We can calculate IC14, which is equals to IC20, and that is equals to 150 microampere. And this is the small current at which class AB output stage is biased, 154 microamperes. So this is how we have calculated all the current and voltage parameters for the second stage and the output stage. Now let's discuss what is the short circuit protection circuitry. That is the part of output stage, and these transistors are normally off. That means they are not conducting. They only conduct when the large output current is required. So whenever the output node is short circuited with one of the supply, like plus VCC or minus VEE, there is a excess current which flow through the transistor Q14 and Q20. If this terminal is connected with VCC or this terminal is connected with VEE, in that case only there is a excess current, and to reduce that excess current we are using this short circuit protection circuit. So these transistors are Q15, 20, 24, 22 along with the resistor R6 and R7. So whenever there is a excess current, in that case these transistors are active, like Q15, Q20, 24 and 22, and when these transistors are active, in that case the some amount of current is steal by these transistors, so that there is a reduction in the IC14 and IC20. So this is how we can reduce the excess current which is flowing in IC14 and IC20 in case of short circuiting, and we can avoid the problem of short circuit using these short circuit protection circuit. So this is the summary. So till now, in my first lecture, we have discussed the DC analysis of bias circuit as well as the input stage. In this lecture, we have discussed the DC analysis of second stage and output stage. So this table summarizes all these current components. So this is the better way to remember all these values, because you know that IC741 is a fixed circuit, it is having fixed circuit, and for the given device parameters, you have to calculate all these values, and the value for any of the transistor is fixed, you cannot change that value. So you can have a look over there, the transistor Q1, Q2, Q3, Q4, these are the identical transistor and the current is same. Q5, Q6, Q7, these transistors are the load circuit to input stage, and here you can see that the Q7 is having different current, otherwise Q5 and Q6 is again having 9.5 microampere value. Similarly Q8, Q9, these are the transistors of bias stage. The Q10 and Q11 is also bias transistor, Q13, Q12 and Q13B, these are the transistors of biasing circuit. This value we have calculated in this lecture only. Q14 is output transistor, 154 microampere current. Q15, Q21, 22 and Q24. These are the short circuit protection circuit transistors, and normally they are off. So if we talk about the DC analysis of short circuit protection circuit, the current across these transistors equals to 0, because normally they are in the off state. Q16 we have calculated in this lecture only. Q17, Q18, Q19, 20 and 23. So this is how we can do the DC analysis of 741 IC. So this is all from my side for this lecture, and it is advised to do the step by step DC analysis of 741 IC. That will be more easier to you for the purpose of understanding. Thank you so much.